Okay, welcome to the first module. We're going to be talking about energy conservation and transfer, and we're just starting from energy. This picture should be recognizable to you. It's from the discussion board that you've probably already commented on, but I just wanted to use this as a primer to start us thinking about energy in the climate system, where it is, and where it comes from. And with that, let's just get right into talking about energy. Um, so, and the Earth gets its energy from the sun, and this solar radiation is the energy source for pretty much everything in the climate system. It is the major source of energy that drives everything on Earth. The Earth gets its energy from the sun in the form of light, which is electromagnetic radiation. And it's mainly in this band of wavelengths, the visible light spectrum that the sun emits at. And the sun emits like a black body, which is just something that absorbs and emits at all wavelengths. And so the temperature of a black body determines the radiation intensity of the energy that it emits, and also the wavelength of maximum intensity. So we know the wavelength of the energy that the sun is emitting. So from that, we know the temperature of the sun, which is pretty cool. So we know that the sun is about 6,000 Kelvin, which is really hot. And so it's emitting at a pretty short wavelength, and it's got a very high intensity of radiation. And this figure here is just showing the black body curve of the sun plotted on top of the ideal black body curve of something that is 5,780 degrees Kelvin. And so you can see that for over most of the wavelengths of energy that the sun is emitting, it pretty much follows very well this ideal black body curve. So that's how we know that this approximation of the sun as a black body is a pretty good approximation. The Earth also emits like a black body, but it's at a really different temperature than the sun. So the wavelengths at which the Earth and the sun emit their radiation are very different. And so here is the black body radiation curve for the sun. And here in red is the black body radiation curve for the Earth. And you can just see that the Earth is all the way down here with its radiation intensity. It's much, much smaller than that of the sun, and you can't really even see it. So here's a little inset showing that indeed the Earth does have a wavelength of maximum intensity. And if we normalize, so yeah, the sun emits way more radiation than the Earth. And if we normalize these radiation curves, so we just divide each value by itself, so the maximum is now 1. So we divide the sun's radiation curve by 6,000, and we divide the Earth's radiation curve by 255. This is the figure that we can get. And we can see that when they're normalized, their wavelengths of maximum intensity are totally different, and that their black body radiation curves barely overlap at all. So that'll be important later on, that the sun emits over here at shorter wavelengths, and the Earth emits over here at longer wavelengths, because it's a lower temperature than the sun. Okay, so we talked a bit about black body radiation, and a black body, as I said, is something that absorbs and emits all radiation at all wavelengths, and the properties of its radiation are determined by its temperature. So we saw that because the Earth and the sun are at different temperatures, they radiate at different wavelengths of maximum intensity, and they also have different magnitudes of maximum intensity. And so there's this relationship between temperature and intensity that we can describe using this equation here, the Stefan-Boltzmann law. And this just tells us that the total intensity of a black body is related to its temperature to the fourth power by this Stefan-Boltzmann constant. Using the Stefan-Boltzmann law, we can then figure out how much energy the Earth actually gets from the sun. And I guess I should mention that this exercise that we're going to step through right now is going to be a way for us to estimate the global average surface temperature of the Earth. So we'll start first with how much energy the sun is actually emitting. So the power of the sun is going to be equal to so we're going to use the Stefan-Boltzmann law, times the temperature of the sun to the fourth. And so that's what's going to give us the power per unit area, surface area. And so then if we want the total power, we're going to multiply that value by the surface area of the sun. And so maybe I'll repeat what that in different words. So to get the total power of the sun, how much total radiation the sun is giving off, we use the Stefan-Boltzmann law to get the power per unit surface area of the sun. So that's the Boltzmann constant times the temperature of the sun to the fourth. And then we multiply that by the surface area of the sun so that we can get the total power coming from the sun. And then the next step is that, so that's good that we know the power coming from the sun, but the Earth is not right on the surface or right next to the sun, right? The Earth is a certain distance away from the sun. And so as we get farther away from the sun, the power coming off of the sun is being spread out over a greater amount of area. So how much energy is getting to this distance here, this distance d, which is distance of the Earth from the sun? So we'll take the power of the sun and we'll divide it by the area, the surface area of the sphere that has a radius d. So it's this dotted line here is kind of just showing part of the sphere. If we can imagine like a bubble around the sun, that it has radius d. So along this sphere indicated by this dotted line, the amount of power emitted by the sun that gets there is equal to what we'll call now the solar constant, S naught. And then that's the power of the sun divided by the area of the sphere, so 4 pi d squared. And that's 1,367 watts per meter squared. Okay, so if at any point you need to pause and think about that, feel free. This video will just be here for you. But yeah, so that is how much energy actually gets to the Earth from the sun. But that is the amount of energy that makes it to the area of that sphere. The Earth only intercepts a fraction of that. So now we'll put in this little Earth, and I made it an ocean planet because I'm an oceanographer. And plus the surface of the Earth is mostly ocean anyways. So the amount of energy from the sun that's intercepted by the Earth is equal to the solar constant times the cross-sectional area of the Earth. So if you were to take a cross section and cut through the Earth, or maybe if you were to think about the Earth casting a shadow on a wall over here, and it would be making a circle, the area of that circle, divided by the total surface area of the Earth is going to be the amount of energy that the Earth is intercepting. So that's, you can just kind of cross out some of these constants, and you end up with the solar constant divided by 4. And so the reason why we do that, why we divide by the surface areas of the Earth, is because every day the Earth is rotating, so both sides of the Earth are actually getting sunlight. So the amount of energy from the sun is being intercepted by the entire surface area of the Earth, but it's only hitting half of the Earth at once. So that's why we take this cross-sectional area and divide it by the total surface area. And that gives us a value of 342 watts per meter squared. So what temperature can we predict for the Earth based on that amount of energy? So we can come back to our Stefan-Boltzmann law, and we take S naught over 4 equal to the Stefan-Boltzmann constant times temperature to the 4th. And so now we'll just solve for this temperature. And so maybe if you want to, you can pause the video for a second and try to solve this equation here for the temperature of the Earth. And you can take this S naught divided by 4 over sigma and take that all to the 1/4 power. So I kind of just did the algebra for you. Okay, and so the value that I get for the temperature is 278 Kelvin. And so 278 Kelvin is about 5 degrees Celsius, which is too cold, spoiler alert. So we're missing something, but we're pretty close. The actual temperature of Earth is about 290 Kelvin, and so we're not all that far off. Yeah, so what are we missing? Well, one thing that we haven't even considered is the albedo of the Earth. So albedo is the reflectiveness of a surface, or the proportion of radiation that's reflected rather than absorbed by a surface. So we actually need to modify our amount of energy that we receive from the sun by multiplying it by this 1 minus alpha, where alpha represents the albedo of the Earth. So the energy balance, or the radiation balance at the Earth's surface between the absorbed radiation from the sun and the emitted Earth or terrestrial radiation now looks like this. It has this extra term here, this 1 minus alpha. And the planetary albedo is about 0.3, so that just means that so we'll just use this 0.3 value for our alpha. And then now we can solve this equation for temperature and see what we can get there. And so I'll just let you plug that into your calculator. Okay, and now the new temperature that I get, if we include the albedo, is 255 Kelvin. And I told you 278 is too cold, so 255 is way too cold. It's about -20 Celsius, so that's definitely way too cold. So we're still forgetting something, or still neglecting something that we need to include. So something we haven't even considered yet is the greenhouse effect. And so Earth's surface, like we've been talking about, it reflects solar radiation, and it also emits radiation. But a lot of that is trapped, most of that is trapped by greenhouse gases like carbon dioxide and water vapor, and also just clouds, which contain a lot of water vapor. So if you think about, like, I live in Seattle, and on cloudy mornings in the winter, those are often warmer than when it's clear out. The clouds and the water vapor are trapping the outgoing radiation, absorbing it, and re-emitting it back down to the surface, as well as out to space. So how do we include that? So now we can look at, we're not changing what's absorbed, what's coming from the sun, but now what we're doing is we're adding this component where the Earth has this outgoing radiation. It's absorbed by the atmosphere, and then it's re-emitted by the atmosphere, both up and down. And so we're just going to do another radiation balance here. And at the top of the atmosphere, all we have to think about is this term and this term. So we can balance those two, and we can find the temperature at the top of the atmosphere in that way. And at the surface, we have a few more terms one more term to balance. So we still have this absorbed term, but then we also have this terrestrial radiation term, and we have this new atmospheric radiation term. So we have this balance between these three terms. And so now we can, using the temperature of the atmosphere, solve for a new temperature of the surface. And maybe I will, if you want to, you can pause the video and solve these equations for these temperatures yourself. Okay, so the temperature for the atmosphere that I get is 255, and the temperature that I get for the surface is 303. So that's good, we've warmed up. However, the bad news is that we've warmed up a little bit too much. So we're still doing something a little bit wrong. So the 303 degrees Kelvin is like 30 degrees Celsius, and that's definitely hotter than the global average temperature of the Earth. So the thing that we're forgetting is that the atmosphere does not absorb perfectly all of the terrestrial radiation. It does let, it's sort of a leaky greenhouse instead of a perfect black body. And so some fraction of the outgoing Earth radiation, terrestrial radiation, just passes right through the atmosphere. And so I have a new term to introduce, and that's the emissivity, or how good of a black body this object is. And so we're thinking about the emissivity of the atmosphere, which is about 0.79. And actually adding or removing greenhouse gases from the atmosphere is what changes Earth's emissivity. So now we just have a couple more terms. So we still have the same absorbed solar radiation term, that's just modified by the albedo. And we still have the same the terrestrial radiation term. And some of that, 1 minus epsilon of that, just goes straight through the atmosphere. But some of it is absorbed by the atmosphere and re-emitted both out to space and back down to the surface. So at the top of the atmosphere, we have a balance between these three terms up here, or so this equation here. And at the surface, we have a balance between this absorbed term and then these two terms, this terrestrial radiation and this atmospheric radiation. And so now to solve for this new temperature of the surface, we just have a few, this might look a little bit intimidating, but it's just, this is the absorbed solar radiation term, and then this is just the atmospheric radiation modified by the emissivity. And then we take the fourth root of that. So the new temperature of the atmosphere, I'll tell you that will equal 242 Kelvin. And so if you want to try to solve for this temperature of the surface, you can go ahead and pause the video now and try to do that. And so the new temperature of the surface that I get is 288 Kelvin, and that's good. That's about 15 degrees Celsius, and that is the global average temperature of the Earth. So we did it. We just had to include the albedo, or the reflectivity of the Earth's surface, and the emissivity, or how good of a perfect black body the atmosphere is, and also the greenhouse effect, to be able to get to that. From the amount of energy or power that the Earth intercepts from the sun. So just to quickly go over that in schematic form, we have the Earth's energy balance is just energy in balanced by energy going out. So this is the energy in component. We have incoming solar radiation. Some of that is absorbed by the atmosphere. Some of that is reflected by the atmosphere. So clouds have an albedo as well, a high albedo. Some of it's reflected by high albedo of the Earth's surface. So places like snow-topped peaks or Antarctica, or even deserts that are kind of light colored will reflect sunlight. And then some amount of that is absorbed by the surface. In terms of energy going out, we have this surface radiation term. Most of that is absorbed by the atmosphere. Some of it just goes directly out to space. And then some of that is absorbed by the atmosphere is emitted back down to the surface and absorbed by the surface. And some of it is emitted out to space. So it's just outgoing long wave terrestrial radiation. And so that's the balance. There's this incoming part that's absorbed by the surface, and then there's this outgoing part. And I just also want to point out that this arrow here, that's back radiation from the atmosphere that's absorbed by the surface, and this arrow here, that's absorbed solar radiation. This arrow is actually larger than this arrow for a reason. So the amount of energy that's absorbed and re-emitted down to the surface by the atmosphere, by greenhouse gases in the atmosphere, is larger in magnitude than that comes directly from the sun. So why are greenhouse gases so important? They pretty much make our planet habitable. Without these greenhouse gases, we did that exercise just now. We saw that without any greenhouse gases, the temperature of the surface of the Earth would be much too cold for us to live the way that we do. And so the fact that this component of this energy balance, this absorbed and re-emitted terrestrial radiation is such a large piece of the energy balance, means that greenhouse gases are really important for our climate. And then to just sort of think about like what happens to that energy after it hits the Earth. This is a picture of the top of atmosphere net radiation. So it's that incoming solar radiation minus the outgoing terrestrial long wave radiation. And we can see that most of the incoming radiation is actually coming in at the equator. And a lot of the outgoing radiation is going out at the equator, but the curve of this outgoing radiation line is a much flatter than the incoming radiation. So actually at the poles is where we get a lot of outgoing radiation, or more outgoing radiation than incoming radiation, whereas at the equator we have a surplus of incoming radiation compared to outgoing radiation. So if we can think about where we think the energy will go. Maybe you can pause and just sort of think about, well, okay, if energy is coming in at the tropics, at the low latitudes, and energy is going out at the high latitudes, what does the movement of energy within the system have to look like? And so that pattern of energy coming in, going out, leads to heat transport from the equator, from the tropics, towards the poles. And so a lot of what the fluids in the climate system, so the atmosphere and the ocean, are doing is redistributing the energy, the heat in the climate system from the low latitudes, from the tropics, towards the mid and high latitudes, or towards the poles. Yeah, and so the next discussion question is going to ask you about the same picture and ask you to just kind of synthesize and think about what we talked about in this module, and think a bit about, well, whether or not we can explain anything else or explain any of the features on this map with a little more confidence than when we were just sort of guessing at what we were seeing at the beginning of this module.